Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to another session of supplementary videos for the course Statistical Thermodynamics for Engineers, and we'll be continuing our problem solving sessions. Okay, so let's start with the problem that we want to tackle. And the problem that we'll be solving is, so let me write down the problem statement first. So the question is, an insulated vessel contains a partition that separates one volumetric region with a monoatomic gas from another region at vacuum. The partition is broken. And the gas is permitted to fill the entire volume the vessel. And there is something which is given. So the given is, if the translational partition function of a monatomic gas can be taken as Z equals 2 pi m Boltzmann's constant times the temperature divided by Planck's constant square power 3/2 E. So that's the translation partition function for the monatomic gas, and given that the question is compute the net entropy change during the process. During the process. So let us draw the schematic of the situation that we are dealing with. So let's say this is the container that we have, the vessel that it's asked. Okay, so this is an insulated vessel and this is insulated. That means the vessel cannot exchange either matter nor energy from anywhere outside this vessel. So it's an isolated system that's given. Okay, and there is a partition in between. And one side contains a gas, a monoatomic gas. Okay, so this is filled with atomic gas. And this is vacuum. Okay, and what we do is we remove the partition. So this is the partition And we remove the partition and the gas fills up the entire vessel. And you see this is a non-equilibrium process, and it will, the moment you remove the partition, the gas will distribute uniformly throughout the entire volume. And the question is, during this entire process, when the partition is removed, calculate the total entropy change. Okay, so that's a classic problem in thermodynamics, and we'll be tackling and solving this problem in two ways. So let's do it first using the partition function, using statistical thermodynamics. So if you recall, the internal energy, let's say U, is given by, in terms of the partition function, is given by n Boltzmann constant t square times the partial of the logarithm of the partition function with respect to temperature at constant volume. Okay, that you recall from our lectures, or our main lectures, from where we saw how important partition function is, and partition function helps us to compute all other thermodynamic quantities. So this is the internal energy, and similarly the entropy is given by the relation U over T plus Kn rhythm of the partition function by the number of particles plus 1. Okay, so those are the internal energy and the entropy written in terms of the partition function, and it's given so what is given that for a monoatomic gas, we have the partition function is 2 pi m kt whole divided by h square power 3/2 v. Okay, so let's take, so in order to take the derivative, so let's take the logarithm of both sides, the natural logarithm. Log z is 3/2 log 2 pi m kt by h square plus log v. And you see, if we differentiate this with respect to temperature, so the derivative of log z, the partial derivative with respect to temperature, is given by 3/2. The derivative of log is 1 over that thing, so this becomes h square divided by 2 pi m kt times the derivative of the argument of the logarithm, so that becomes 2 pi m k by h square, and the derivative of t with respect to t is 1. Okay, so basically h square gets cancelled, and we are left with 2 pi mk gets cancelled, 2 pi mk gets cancelled, left with 3 over 2t. Okay, so the internal energy becomes 3 over 2t. That's the partial derivative of log z with respect to t multiplied by n Boltzmann constant t square. So this simplifies to 3 over 2 n Boltzmann constant t. So that's the internal energy. That's the internal energy at a given temperature T for the particles. Now, since this is an isolated system, that is for isolated system, there is no energy exchange either in form of matter or in terms of work done or heat. So therefore the internal energy change, as you can see, is 0. It tells us that the temperature change is 0, and since no matter exchange is occurring, there is no change in the number of particles. Okay, so therefore the entropy change, if you see using this equation, so if U doesn't change, T doesn't change, K is the Boltzmann constant, N doesn't change. The only way the entropy can change is when the partition function itself changes. So therefore delta S, the change in entropy, becomes Kn log of Z2 minus log of Z1. Okay, that's the change in entropy in terms of the partition function. And the logarithm, we've seen that is log Z is log V plus 3/2 log 2 pi mkt by h square. And if we do it for the two states, the end state comes v2 plus 3/2 log 2 pi mkt by h square log z1 1 plus log 2 pi mkt by h square. And therefore we have log z2 minus log 2 minus log z1 is nothing but log v2 minus log v1. The entropy change S could be written as n Boltzmann constant log v2 minus log 1, or it could be written as nk log v2 over v1. And since it was initially half filled, half filled initially, therefore we have the v2 is twice of v1, therefore v2 by v1 is 2, so this becomes, therefore v2 by v1 is 2, therefore the entropy change as when the process becomes nk log 2. Okay, so that's the entropy change in terms of the number of particles, Boltzmann constant. Okay, for the process that we have, where initially there was gas in half of the container and a partition was separating it. When we break the partition, the gas fills the entire vessel, and the entropy change is given by this. Let's see whether we can come to a similar expression from classical thermodynamics point of view. Okay, so let's say from classical thermodynamics, let's use the TDS equations. Is given by du plus pdv, and since du is 0, it's an isolated system, and assume an ideal gas, we have, let's say, pv is equal to nRT, where this is the number of moles. This is the ideal gas law. So using this, we can write ds becomes p over t dv, and p over t nothing but nr by v dv. Therefore delta is equal to nr dv by v from 1 to 2, so nr log 2 by v1, and just now we saw v2 by v1 is 2, so this is nr log 2. Okay, and realizing the fact that the universal gas constant can be written in terms of the Avogadro's number, Na times the Boltzmann constant, K, and the Avogadro's number is n divided by the number of moles. This is the number of moles. This is the total number of particles, and this is the Avogadro number, Avogadro's constant. Okay, so using this, what we have is Na R can be written capital N by small n times K, or capital R times small n times K. So if you see it, here we had NR, but NR as we saw is same as NK. That means delta S NK2. And if you recall from statistical thermodynamics, we come to the similar. Compare this with this. Okay, so that gave us the expression for the total entropy change during the expansion process. Okay, when the gas occupied initially half volume and then expanded after the removal of the partition in between. Okay, good. So now we'll be seeing the next problem. Okay, so let's continue with another problem. So the next problem is, let me write down the question statement. So this is related to paramagnetism. So paramagnetism can occur when some atoms in a crystalline solid possess a magnetic dipole moment owing to an unpaired electron with its associated orbital angular momentum. Angular momentum. So that's what paramagnetism is. This is a concept in condensed matter physics. And let me complete the problem statement. So for simplicity, assume that number one, each paramagnetic atom has a magnetic dipole moment, mu, and two, magnetic interactions between unpaired electrons, can be neglected. Okay, so therefore when a magnetic field is applied, the magnetic dipole will align themselves either parallel or anti-parallel to the direction of the magnetic field, or anti-parallel to the direction of the magnetic field. Okay, so let's say if the magnetic moment is parallel to a magnetic field induction B, the potential energy is minus mu B, and when the magnetic moment is anti-parallel to B, anti-parallel to B, the potential energy is plus mu B. Okay, where B is the magnitude of the magnetic field. Okay, the question is calculate the probability. Calculate the probability for an atomic magnetic dipole moment to point parallel to the magnetic field, to the magnetic field at temperature T. Temperature T. Okay. It is also given that we use this grouping x is mu B by kt. Okay. So let's see how we tackle this. So it's given in the problem that using the simplified assumptions that independent unpaired electrons, of dipole moment, paired electrons of dipole moment mu in magnetic field B. Okay. So the independent magnetic dipoles have access to two energy states, so there are two energy states. So the independent magnetic poles have access to two energy states. Epsilon 0, that is minus mu times b, and epsilon 1, that is plus mu times b. Okay, so let's construct the partition function. So the partition function z is given sum over I e to the power minus epsilon I by k times t. So therefore the partition function z becomes e to the power mu b by kt plus to the power minus mu b by kt. Okay. So now therefore the probability of magnetic dipole moment pointing parallel to magnetic field is given by P. Let's call that state 0. It's parallel because when it is parallel it has the energy state of minus mu b. It is anti-parallel, it's plus. So that corresponds to the 0th energy state, which is this. So this becomes e to the power mu p by kt divided by the partition function, and therefore let's use the grouping mu b by kt, call that x. So this becomes e to the x, and the partition function therefore becomes e to the x plus e to the minus x, and therefore let's divide the numerator and denominator by e to the x. This becomes 1 over 1 plus e to the minus 2x, and therefore this could be written as 1 plus e to the minus 2x all to the power minus 1. Okay, keep in mind that x is the group mu b by kt. Okay, so let's see. So for, let's say, for t tends to infinity, this means x tends to 0, and if x tends to 0, p0, this becomes 1 and p0 becomes half. Okay, and let's say for t tends to 0, x tends to infinity, and that implies p0 so this x tends to infinity to the minus input, this becomes 0, so this becomes 1. So what this two limits of temperature is telling us is that for very low temperature, that is for t tends to 0, all magnetic dipoles are in their lowest energy state, that is in their ground energy state. Okay, and for very high temperature limit, that is for t tends to infinity, the magnetic dipoles can be in either energy state with equal probability. The probability that we computed was half, with equal probability. and since there were two states, the probability was half. Okay, so that's the end of this problem. So you see, we used a very important idea. So the main idea was computing the partition function. So in most problems in statistical thermodynamics is related to computing the partition functions. Once you know the partition function, rest everything follows basically from there. Okay, so that's what that's for this segment, and we'll be seeing you in next segment. Okay, thank you.